Hello, and welcome back to a new unit. The unit that we're going to be dealing with doing today now is going to be on vectors and how they apply to projectile motion and things like that. So, what's the difference between a vector and a scalar quantity? Remember, a vector has something extra. It's got a direction associated with it. They both have a magnitude, but only vectors have a direction. So different things that we can represent by vectors, meaning something that's got a direction. We recognize displacement, which is how far you end up from where you started and which way. We can talk about velocity as a vector, which is the magnitude is the speed, how fast, and the direction is which way. We can talk about acceleration. That's the rate at which your velocity is changing, and the direction is, of course, which way that is directed. And forces can also be represented as vectors. The magnitude is how hard or how strong, and the magnitude or the direction is which way you're being pushed or pulled. So we can represent vectors many different ways. We could talk about the direction as far as up, down, left, or right. We can use compass directions, never eat soggy waffles, right? North, south, east, west. We can talk about the angle in degrees. We start with 0 degrees and then 90, 180, 270, which we won't use this specific way. We can use Cartesian coordinates. We can say to the right is positive x, to the left is negative x, up is positive y, and down is negative y. Or we can just use an arrow to represent a vector as a picture. And there's certain advantages to doing this, and we'll see. So different ways I can all represent the same thing. 3 meters to the right, 3 meters east, 3 meters at 0 degrees, okay, plus 3 meters in the x direction, and 3 meter as an arrow, which this arrow isn't actually 3 meters long. I would have to use a scale like on a map. Okay. So we can add scalars. 3 apples plus 5 apples equals 8 apples, and we can also add vectors. But 3 plus 5 won't always equal 8. Only in certain situations does it equal 8. You might say, how can that be? Well, I'll show you. So when we add two scalar numbers, the answer is called the sum. When we add two vectors, the answer to our addition is called the resultant, which you should recognize from the book reading. I'm sure they talked about the resultant. So the easiest scenario you can deal with is adding vectors that are parallel. So let's say I've got two arrows here, and are those arrows parallel? They look it. Are they parallel now? They look it. Are they parallel now? No. What about now? No, they're perpendicular. What about now? Yes, they're parallel. So vectors that are parallel can be added very easily, and I'll show you how. So let's say we walk 3 meters to the right and then 5 meters to the right. My resulting displacement is going to be 8 meters to the right. You just added two vectors without even knowing it. 3 plus 5 equals 8, okay, to the right. The 3 plus 5 does equal 8 in this situation. So the resultant is an arrow that stretches from start to finish. Now this, I didn't put it on top of this so that you could see those vectors still, but technically this would be on top of that, starting from start to finish. And the answer is called the resultant. Now let's add 3 plus 5, and we will not get 8. We're going to add 3 meters to the right and then 5 meters to the left. Okay, where is my displacement? What's my displacement going to be? Well, from start to finish, it's going to be 2 meters to the left. So here, 3 plus 5 equals 2. You might say, well, you didn't add 5, you subtracted it. Well, we did add 5. We added a negative 5. So if this is plus 3, we add to that a minus 5, we end up with minus 2. And the negative just means the direction. And minus 5 means 5 to the left, and minus 2 means 2 to the left. So when your vectors are parallel, all you do is just add or subtract the numbers, just like you would do rationally, I think. There's nothing too big of a deal with that. We can also add velocity vectors or speed not speed vectors, velocity vectors. So if you think about that conveyor belt in the airport, if you've ever been to the airport and seen the conveyor belt that you walk on and it makes you walk super fast, those are pretty cool. And those are an example of adding velocity vectors. So there's three velocities. There's your velocity relative to the walkway. There's your velocity relative to the ground, and there's the walkway's velocity relative to the ground. So there's three different velocities going on here. So when you walk with the walkway, you're adding two positive vectors or two negative vectors, and they combine, they add up because they're in the same direction, and your speed increases. When you walk against it, you're subtracting vectors. Okay, so here we've got an airplane that can fly 60 kilometers per hour in still air, if the air is stationary. Now, if it's flying along and along comes a tailwind at 10 kilometers per hour, the air relative to the ground, okay, the plane is going to speed up relative to the ground. So it's going to be traveling at 70 kilometers per hour. So that's the resultant. Again, they're parallel, so we just add or subtract them. Then let's say our airplane does a U-turn, and now it's pointed south, and now it's flying 60 kilometers per hour south relative to the air. The wind is blowing 10 kilometers per hour north, so its resultant velocity is going to be what? It's going to be 50 kilometers per hour south, okay, or negative 50 kilometers per hour. So if we looked at the signs, we would have negative 60 kilometers per hour plus 10 kilometers per hour equals negative 50 kilometers per hour. And that would be just another way of saying 50 kilometers per hour south in this case. All right, so adding perpendicular vectors. This is a little bit different. And by a little bit different, I mean quite a bit different. It's not hard though. So when they're parallel, you add or subtract them. Simple addition or subtraction. But when they are perpendicular to each other, we got to do something different. So if you walk 10 meters to the right and 6 meters to the right, you end up 16 meters away from where you started. If you walk 10 meters east and 6 meters east, you do not end up 16 meters away from where you started, do you? I don't think so. That, and just to show you, I have this all to scale. So that red arrow, we're less than 16 meters away from where we started. Okay, where would you be? Okay, well, what we can do is finish off this parallelogram. So what we do is retrace the 6 meters, we trace it over here on the right, and this 10 meters, we trace it up at the top. Okay, notice that there's a starting point, the beginning of the vectors, and then I follow the arrowheads, and I end up here. And I start and finish in the same place if I take the other path. I can start, follow the arrowhead, and end up here. The resultant, which is in this case the sum of these two vectors, is a vector going from start to finish. Okay? So if we were to be drawing this out, you would just draw this arrow, and that would be the resultant from start to finish. And then there'd be a couple different ways that we need to represent the resultant. Okay. One, you're going to be using a scale, so don't count boxes because boxes get wonky if you do the diagonal. That is, if you're using graph paper. And I'll show you what I mean by the scale. So the magnitude is we're going to measure this thing, and we're going to see how long it is, and we're going to use a scale like a map. And in this case, I'm going to get 11.7 meters. And then I'm going to represent the angle with the direction with an angle. And the symbol we use to represent an angle in physics is this theta. And that it's just a Greek letter. So anyway, it means the angle that we're talking about. So we would measure that with a protractor. So you'll need a protractor and a ruler for today's activity. Hopefully you have those on hand. Okay, so let's work an example. We're going to add 8 meters west and 19 meters south. We're going to do this, and you want to do this on graph paper if you have it. If not, you can make do with regular paper, but it's a little easier with graph paper. So the first thing we want to do is come up with a scale that's going to fit on my graph paper. And I came up with a scale that 1 centimeter equals 2 meters. Okay, that means that means this 8 meters, since 1 centimeter equals 2 meters. Okay, 8 meters, and then I multiplied by my scale 1 centimeter over 2 meters, because the left equals the right, so I can multiply this without changing the quantity, because I'm using the top equals the bottom. It's like multiplying by 4 over 4. So I'm going to divide by the 2, and I'm going to get 4 centimeters, and that'll certainly fit on my grid. And then we've got 19. I'm going to use the same process. 2 meters equals 1 centimeter, so I divide by that, and I get 9.5 centimeters, and that also fits on my scale. So what I'm going to do is draw those vectors. I draw 4 centimeters west. Okay, I pick a starting point. Now, first off, I know I'm going to go west and south, so I started north and east. Okay, so I started in the northeast corner here. That way I'm going to have room. If you'd started down here, you would have run out of graph paper. So 4 centimeters west. And then I drew my 9.5 centimeters south down. Okay. Then I transferred this one over. I went from, and again, I'm going to draw this one from the tip of this one. I'm going to go down 9.5 centimeters. And then from the tip of this one, I'm going to go 4 centimeters west, and I'm going to end up here. Now, the resultant is from start to finish. Okay? If you start at the arrows and then follow them, you end up at the finish. So now I measured this arrow, my resultant vector, and I found that it was 10.3 centimeters long. Now I want to know what the answer is in meters, though, because that's the question. So I use my scale again, and this time I multiply by 2. So 1 centimeter equals 2 meters, okay, and I get 20.6 meters. And then I use my protractor and I measure this angle. You could have measured this angle here too. It would have been fine. I just measured this angle. But you want to measure the angle compared to the resultant, okay, and I got 67 degrees. Okay, so not a big deal. You got to come up with your own scale on these. Just come up with something that's not too small. If it's too small, you're not going to get accurate results. If it's too big, then it's going to not fit on your paper. So you just have to kind of use your graphing skills to figure out what's going to work for that. Okay. Well, if your vectors are also perpendicular, and those are the only ones that we're going to be dealing with in this today anyway, we can also use Pythagorean's theorem to find the resultant, because the resultant is the diagonal, the hypotenuse of a right triangle. So remember, a right triangle, in order for this to work, you must have a 90-degree angle. Okay, and the longest side of this, which is always across the 90-degree angle, is the hypotenuse, and then you've got side and side. Okay, so which side is the hypotenuse? Okay, it'd be that side, and that side. Okay, the longest one. Okay, the diagonal one. Okay, and Pythagorean's theorem is a squared plus b squared, where a and b are sides, equals c squared, where c is the length of the hypotenuse. So super easy. You guys have been doing this for a while. So let's work in a quick example here. We want to figure out the hypotenuse, which we'll call C, or we call it R for resultant or whatever. So what we get is 3 squared plus 4 squared equals C squared. Okay, so that gives me 9 plus 16 equals C squared. And then that we get 25 equals C squared. And lastly, we get 5 equals C, or C equals 5. So this is a 3, 4, 5 triangle. It's a special case where the numbers work out really easy, but the same process is used on the other triangles too. Just the numbers don't work out as clean. Okay, so let's work one more of these examples. Here we've got a plane. It's flying 75 kilometers per hour due north, and the wind picks up blowing 25 kilometers per hour east. Now this is north and this is east. These are not parallel, so I cannot simply add or subtract them. I've got to draw them out. Okay, what is the velocity of the plane relative to the ground? So basically what we're looking for is the resultant of these two vectors. Okay, so step one, figure out a scale. Okay, and I used a scale that 1 centimeter equals 10 kilometers per hour. That means that if I follow the same process, 75 kilometers per hour, okay, times 1 centimeter over 10 kilometers per hour, it gives me, basically I'm going to divide by my scale to get it into centimeters. So I get 7.5 centimeters. And then I'll divide by my scale here and get 2.5 centimeters. Draw it out, 7.5 centimeters north, 2.5 centimeters east. Okay, draw that same 7.5 centimeter north up here, and draw that same over here. Okay, and then draw the resultant. Now, one thing that I want you to do, if it tends to get a little bit messy with the arrowheads, over here. If you just want to, because I'll give you points for showing me that your vector is in the right direction, draw a little arrowhead back here, just so I know that you got it going the right way. So just do that, please. So and we got, so then we measure it, and we got 8 centimeters. That is what I got, which is 8 kilometers per hour, 80 kilometers per hour using my scale. I got theta. Theta equals, it won't show me, theta equals 76 degrees. So how do you know which angle to use? Again, I start from the beginning of the resultant. The resultant starts here and ends up here. So start at the beginning of the resultant and just pick one of these vectors. I chose this one. This because it was easier, I think, with the protractor. So 76 degrees. And then compare that to Pythagorean's theorem. We get r squared equals 75 squared plus 25 squared, and that gives me, 79 kilometers per hour. So we got 80 by doing it graphically. The correct answer is 79. We did pretty good. But one thing to note is Pythagorean's theorem does not give you the angle. So you've got to know a little bit more trig for that. So anyway, that is that. So go ahead and do the worksheet. There's a couple things to do on the back, and yeah, good luck.